and thank you for staying at the last talk today. It's always hard. We would like to say a few words about generative models. What is it, how to do it, and why it's, in our opinion, important. So let's start with the definition or concept. What is a generative model? And the generative model is the object or the aim of the generative models is to construct objects similar in some sense to existing ones. So we often assume that we have some kind of objects, we have a lot of objects, some kind of data set, and usually want to build new similar object to that which we have. So this can be used, for example, for data augmentation. The other kind of generative models, which is maybe more interesting but slightly harder, is the idea to construct objects which are different but somehow similar to those we know. And the idea of generating objects which are similar to those we know is very common in the biological life. So if you, for example, if I ask someone from you, please imagine a dog. Everyone of you have an instant an image of a dog. Then I can ask, okay, can you have this dog brown? Okay, can the dog wag its tail? And immediately a human being can construct an object which you are interested in. So this biologically constructing objects which are similar to what we see is important. And in the case of computer science, this kind of implementations is called GAN. It's Generative Adversarial Network. So we will speak in the second part of our talk. Przemek will slightly more say about it. But how it works, look here. So you have some pictures, and all these pictures were constructed by artificial networks. These are kind of state of the art, so some of the best pictures which you can find. But as you see, they are almost real. So if you look very closely at this dog, you can see that with his legs, they are not perfect, okay? But you have to look closely. Also, this mushroom is also not so ideal, but this look really, really good. So to obtain such object, you have to build a complicated network, put it all the internet, and then it can produce something like this. Generating not similar data, it's maybe more interesting and more fun. Why? It's all our thinking or science or art is generating new ideas, new things which we haven't seen before. So I think that people also are very good at this kind of thing. For example, I can say, imagine big brown dog with 6 legs, and everybody of you can draw with such a dog very easily. So this for a human being, so from evolution point of view, is also important. Why? It's good for abstract thinking or working in environment which we don't know. So it's the necessary of evolution to adapt to changing conditions force the human brain to have this ability. I think that also some higher mammals or higher birds can do it. The computer science analog of this, they are not so, in a sense, abstract and intelligent as human, but you can call it style transfer or transfer learning. In the simplest case, the idea could be to take 2 models or 2 objects and try to mix them to obtain something new. But of course, there are some other cases where you can obtain such an object. Przemek will also show something like this, but I will just show you some pictures which could be. It's mainly from Deep Dream of Google. But if you look at these pictures, there are usually some kind of mixtures. So these are some pictures which were constructed by neural networks, but they are not real in a sense. You usually can't see such objects in the reality. Okay, so these are some maybe also other nice objects. So this is the case when you obtain something new by gluing together usually two two known objects. Okay. But of course, you can obtain something like this also by mistake. So if you look at these pictures, they're also very nice because they are made by very good generative networks, which try to learn to generate, let's say, elephants or bears. But as you see, they are not completely right. So if you look at this object from a local point of view, everything seems fine. But if you look like a human and try to see what is this, you somehow see that this elephant is not exactly right. So maybe you can find at home, if you are interested, some other examples where similar research happens. So this is an example of the situation when you have program which is supposed to be good, but sometimes it doesn't have very good results. Not always makes good results. Okay, so we have some kind of brief introduction to the subject of the generative models, and just a few words maybe about how humans do it. We don't know everything, but just a few words, and then we'll try to say slightly more about how computers do it. When did everything began? So it's about 1 billion up to 500 million years ago. The evolution of neurons started, and there are some suppositions that the neurons were not once invented by nature, but many times. There are various versions of neurons, so we have different kind of neurons than octopus. But if you look at when in the genotype some kind of ion channels appeared, which are necessary for the transfer of neurons, then it's about 500 million years ago. So this is the beginning of the neural networks, as we can see biologically. Neuron, probably you can see this. You have seen this picture many times. Joins the neuron joins by the axons with other neurons. Then you have synapses, and it can contact with other neurons. So if you have one neuron, in fact, it can do something. It can do some kind of simple classification if you have tried it. But in fact, something interesting happens when you look slightly at bigger structures. And the first neural network which we are sure existed is the network which is in the eye. Okay, so what you see here is about 500 million years ago appears. It's 2 layers of neural networks. So you have cones and rods which are to the right. They are photoreceptors, but you have 2-layer neural networks. And in fact, most of the networks we apply here. So this shows the complexity of the brain, that most of the networks we do in artificial intelligence is this. Of course, to some extent, it's not 2 layers by 500, but most of the networks are feed-forward layers and sometimes convolutional, but this kind of networks can be seen as slightly convolutional. So this is more or less what have people adapted from the biology to the artificial networks. Okay, and then what happens later? The brain evolves, and as you see, adapts and modifies and grows and adapts and constructs many substructures. So if you look here, you have brain of sapiens, and human brain is one of the biggest. This is the upper right slightly, and in general, you have also specialized structures for processing different kinds of data. So the same we do now. So if you want to process images, we use convolutional networks, but for other type of data, you use different specialized networks. And so this is the end of story from the biological sense of view. And in fact, we still don't know how human brain works. So we don't know how it learns, by what method it learns, and it's not easy to describe why and how human brain resolves problems. But we can now describe what we know much more about, that is the artificial networks. And the invention of our artificial network was single neuron. It was around 1950s, and it solved some kind simple problem classification of letters. What was used? It was the construction of one simple neuron, and this neuron, in fact, is very similar to the classical biological neuron. So we have inputs, and we weight these inputs by some weights, and if this weighting is bigger than some lever, threshold lever, the neurons push forward some kind of signal. So this is this is the classical neuron. It occurred that this is not so easy to teach because this activation function, so the step function is not differentiable, and that's why people change it. And now it's commonly assumed that the best function which is used for as an activation function is the ReLU activation function. It's going to rectify linear union. So this is the basis on which all neural networks now currently work. And what do you do next? You apply exactly the same idea as was in the retina in the eye. So you put layers and layers of such networks. So this is the simplest idea what happens next. You try to put layer, first input, then some hidden layer, can be a lot of hidden layers, and then you have output. So now just a few words about how we teach these neural networks. In the case of, as I told you, in the case of biological networks, the mechanism how these networks learns is unknown. In the case of artificial networks, the situation is rather simple. We need, in fact, two objects. First, we need to know what we want to minimize. So we define something like cost function, and in this case, suppose that we want to solve a regression problem so that we have a point xi and yi, and we want to construct the function f which maps xi into yi. So this is a typical regression problem. And then what you do is say, okay, I measure the error, total error of this approximation, and this total error I understand as the cost function. And depending on the weights omega, it can be smaller, greater, and I try to minimize it. So I try to find such weights omega for which this cost is the smallest, and the cost is the smallest means that I have the optimal approximation. So here is easy. The situation is easy. And then you do what? You simply go down. So if you have a cost function which depends on weights parameter, then you try to move, and you have the cost function, you try to go down with the cost. And going down with the cost is very simple from the numerical point of view. You compute the gradient, which you can compute by the backpropagation automatically, and you go down. And going down leads you to some kind of minimum, local minimum, but anyhow you get it down, and then this is the solution which you arrive at. And one last thing, which is some kind of basis which you need to know about gradient descent, that computing this sum, as you say, over all data set is very costly. So if you try to compute this cost function over the whole and minimize this cost function over the whole data set, you would have to compute over possibly millions of examples. And first, this is very costly numerically, but anyhow, the results are not the best. What people invented or observed, that it's better at each iteration step not minimize over the whole data set, but you sample a portion of this data set, it's called mini batch, and you minimize this function over the small sample, and then next iteration you choose new sample, and so on. And it occurs that in such a manner you obtain even better minimization results than by applying this cost function to the whole data set. So this is almost all which you need to know about minimization of the neural networks. But as I told before, if you want the neural network to work well on your data set, it has to be the architecture has to be data oriented. So the architecture cannot be arbitrary. So this is what I show here is a fully connected feed-forward network. Fully connected means that from each neuron, there is a connection to every neuron in the following layer. As you see, in such a case, you have too many weights, and the model is not so. For the model, it's not so easy to learn because the number of weights could be bigger than the number of the data, and so that's the problem. So what you want to do is your aim is to adapt your network to special data. And there are two most common architectures which are used. There are much more in practice, but these are two most common. These are recurrent networks, and recurrent networks are used for processing of the natural language. Namely, they have some kind of memory, and they have kind of recurrent connections. So this is the same as humans. We have some kind of recurrent connections, which means that the neurons can, the signal can come back to the same neuron many times. So usually they are best for kind of LSTM and or group. What we are interested in our group more, they're convolutional networks, and they are applied mainly for image processing. So the convolutional networks apply local convolution, but the same convolution to each part of the image. And it occurs that such a method is very good with respect to results, and the amount of weights, because they are local, is much smaller. So we summarizing, we go through the whole picture with the same filter, and the filter aims to learn features which are interested in. So this is the convolutional neural networks, and now Przemek will.
Okay. The second part of our talk will be concentrated on a new generative model which was constructed by our research team. The paper idea is as fresh as possible. In general, we don't have any preprint yet and any repository on GitHub, but we plan to finish our work in next few days. In general, we start from classical feed-forward convolutional neural networks. The final model is a little bit complicated. I try to clarify every step in our method. In general, feed-forward classical convolutional neural network is a simple construction. First, we put directly our image to the model. Here we have grayscale image with size 28 by 28 pixels. And after that, we have a few convolutional layers. In general, idea is that we resize shrink the image. In the next layer is 24 by 24, 12 by 12, 8 by 8, and in general, the representation is deeper. At the end, we have to construct a cost function, classical softmax with cross entropy. In general, convolution is a quite simple idea and exists in literature for many years. In general, we have an image, in our case grayscale, and the mask. We move the mask through the image and we make apply the convolution. We simply multiply the element of image which is covered by element of mask and sum up this, so we have 0 multiply 4 plus 0 multiply 0, etc. And the result is produce the representation of our image in the next step. Here I show you that it is possible to construct the representation with the same size. If we want to have the same size, we have to add some padding, some additional elements in our convolution, because if you don't have any additional element, you are not able to put your mask in the corners. And if you extend our image, fill in them, for example, by zeros, you are able to construct the representation with the same size. Of course, you can shrink the output. We can do it by many different ways. In general, we can move the windows not by one element, but by 2 elements or more. Of course, we can use pooling and other methods. In general, it is possible to produce the output which has lower dimension. Of course, we can do it in the reverse way. We have input with 4 pixels, and the output is a 5 by 5 array. In such a way, we have to add quite complicated paddings, fill them with zeros, and thanks to it, we can extend the size of the output. It is called the convolution or transpose convolution in literature. Of course, if you need to construct the deeper representation, you can use more mask. One mask produces one layer in the output. So if you want to have 10 of depth, you can use 10 filters. What convolution do? Convolution extracts some information from images. For example, we are able to produce the edges from images or find the edges. We can extract the more sharp images. In general, we can do a lot of different transformation. Here we can see how it works in practice. The left-hand side image contains our image. Here we have some mask, and this is the produce of our convolution. We can change the mask. For example, we can find horizontal edges, etc. What deep neural networks do? In general, they train the weights of the convolution in such a way that they extract some information, for example, edges or some gradients or some blur or some other elements, which are good for the target cost function. And in general, we can notice that different layers in our convolutional architectures correspond with some features. It is quite known that the first few layers describe some simple elements like edges, line, gradients, but the last, some further layers contain some more complicated features. For example, a style, and we can do some style transfer. We need two images, one with the style, for example, Van Gogh image, and one simple image which we make by our camera, and we can frozen the layers, the weights of our convolutional neural networks, and on some layers we can move one image in such a way that is as close as possible to the our target style image. In consequence, we can transform our image in the Wasowski style, Van Gogh style, Munch style, and etc. Okay, but we try to construct a generative model. We can say the generative model, as it was described by Jacek, it is a model which try to produce similar elements to the elements from the training data set, but not exactly the same. In general, we would like to train, to model the manifold of data and the distribution of data in such a way we are able to produce new element. The classical example is the data set of human faces. We train our model, and we would like to produce new human faces, which look like a human. We have eyes, ears, mouth, etc. But the faces is not similar to any elements from training dataset. And there exists a lot of different algorithms for doing this. Wasserstein autoencoder, variational autoencoder, generative adversarial networks, autoregressive model, etc. In our talk, we would like to concentrate on GANs, generative adversarial networks, because they are famous of producing very sharp images. I show you some examples. I hope that most of you see something like that. First example is the human faces. This is a program. As we can see, the model produces very sharp images with human faces, and I hope no one can say that it is not that it is impossible that this kind of people are real real person. In the context of producing human faces, we very often make some interpolation. Interpolation is quite easy. We take 2 or more photos and try to approximate the smooth transformation of one image to the another. If the generative model is well trained, the transformation is good. For example, if we interpolate between some person with short hairs and long hairs, we should to see how the length of the hair is changing. The second example is the famous cycle guns. It is famous because almost everyone see that it is possible to change zebras to horses and horses to zebra. Of course, we can change the summer to the winter, winter to the summer. Of course, we can change the style. We have some image, and we can make some Monet, Van Gogh, Cézanne style of our image. Of course, we can do it also on some movies. Here we have the transformation of horses into zebras. We can transform real world to the world of computer games. We can also change day into night. You can find many funny applications of guns in internet. I would like to show you one more. This is a map of guns in general. The first gun is a vanilla gun, and we have the gun here, which was constructed by Goodfellow. After that, we have DC gun, so the convolution gun, which use convolutions. Then we have cyclic guns, which produce zebras. Pro guns, which produce the human faces. Self-attention gun, which use self-attention idea. After that, we have big guns, which was constructed also by Goodfellow. And the last step is style gun, which use almost every idea from previous guns, and nowadays produce the most impressive images now. Okay. Let's describe the architecture. In general, the goal of our model is to produce a generator. Generator is a network which produces fake images, so the images are similar to the images from training dataset, but not exactly the same. The idea is simple. We produce some Gaussian noise, and the Gaussian noise should be transformed by the model, by generator, into real world image, which is almost the same like the image from real camera. How it can be done? In general, we force the generator to construct the proper images by adding discriminator, and we make some games. The generator try to generate images which are as close as possible to the images from the training dataset, and discriminator try to discriminate it is a fake image or original image from training dataset. The cost function is quite easy. The first part describes the ability to discriminate elements by discriminator. The second part of our cost function describes how a generator produces good images. We train them one by one. First, we train generator, after that discriminator, and again generator, and again discriminator. GANs, and I show you, produce very sharp images, but they're extremely hard to train. Why? Because it's the problem with the competition. Because when discriminator is very well at the beginning, he wins very quickly, and generator do not produce anything. On the other hand, if generator wins very quickly, the discriminator is poor, and generator is able to win the games by producing only one image. Very simple, and in consequence, we don't have a generative model. Of course, if you are able to train the model in such a way that generator and discriminator in each step is on the same level, at the end, generator fail, and discriminator failed, and generator will be our generative model. Our work is concentrated on producing high-resolution image. It occurs that there is a problem with producing high-resolution image because, you know, if you have a high-resolution image, the discriminator has a lot of pixels which can be used to win the game. And it is quite hard to help the generator to make a competition. The solution, state-of-the-art solution, is a program. Program is a quite simple idea. First, we train our model on small images, for example, 64 by 64. When you finish the training and you are able to generate some small images, you add another layer to produce larger image, and you train it again. And after that, you add another layer, and again you train the model. Finally, you are able to produce high-resolution image. Unfortunately, such a model has some problems. The first one is the training time, because you have to train a lot of models in different dimensions. And the problem is that you use a different architecture for different size of images. Our solution is quite simple. First of all, the main idea is that we try to train our model, one single model, on some small parts of the image. In general, we fix some size and cut randomly elements from the data and try to train fully convolutional GAN. It is important to say that it should be a fully convolutional. When you finish your training, it occurs that you are able to produce image with any resolution, with any size, by changing the size of the noise which is put into generator. To understand the idea, you can focus on very simple relation. In general, if you have fully convolutional neural network, so you use only convolutions, you don't have any fully connected layer, you have simple relation. If you put to your model large input, you obtain large output. If you put in your model small input, you obtain small output without changing the weights, because the convolution layer depends only on weights. So you have some mask, you can train the weights of the mask, you move them through the representation of image, and the result is with a proper size. So in general, we can train a small model with different elements from data, and after that, you only change the input. You put here larger noise, and you are able to construct the final image. Of course, it is hard to do it if the model never see a whole image, because when you train them only with some patches, some parts, it is quite hard to know where the eyes should be or where the mouth should be. So to solve this problem, we add to the model two kinds of information about location. The first one is that in each layer we add two additional layers which contains the position of the images. I present here it on the input layer, so we have some image in RGB format. And in general, if we have classical convolution, we do the convolution with some ways, and we obtain the output. In our case, we add 2 additional layers, which contain the position. So for the first pixel, on the first layer we have 1 because x-axis is 1, and on the second layer we have 1 because y-axis is also 1. For the second pixel, we have the represents the first layer 2, and on the second layer 1. We add it to any layers with also in discriminator as well a generator. The next step is that we add also the full image, which is resized from time to time. We add to the model a full image, which is resized to the size of the element which we cut, and we also resize the coordinates of the elements. And this is a final model. We can see our result. This is a version 1. At the beginning, we obtain this kind of faces. As you can see, they are not perfect. It occurs that problem was in the padding. We add 0 padding, and it occurs that these zeros influence our model. So in the next step, we solve the problem, and it occurs that it's helped. Some of these faces are better. But still we have some problems, and it occurs that training of GANs is quite complicated, and you have to use all modification which was done through last 5 years. So you have to change the cost function to the Wasserstein GAN, you have to add spectral normalization, you have to use different learning rate for discriminator and generator and some others application, and when you do something like that, you can obtain something like this. And I hope you agree that some of these faces, for example, here, looks like real human beings. We still modify the model, and we are almost sure that in next few days we obtain a really sharp images. Thanks a lot for your kind attention.
Thank you very, very much for your presentation. And now it's time for your questions. So let's see what we've got here. The first question from Diana is, who has copyrights of the photo art created with generative model?
I believe that no one. I believe that no one, because up to my knowledge there not exist any law or something regulation what happens when deep neural networks architecture produce something.
Okay, does it satisfy you, the answer? Yes? Okay. So the second question with the highest votes is, how long it would take to teach machine how to create inputs for the test? Is it measurable?
Okay. I think that the answer is it's not long, but you would have to, because if you would use the generative models, you have to have many inputs. So if you would have, let's say, 1 million inputs, then you could create new ones probably. But the problem usually with generative models is the amount of data. So the deep learning still needs to work well a lot of data. So that's why we work with images, because there are millions of images in the net.
Okay, thank you very much. Let's see the third question from our audience. Is it possible that GAN we've created similar but not true case will strive to trolley problem, and we will need to learn AI what is morality. Hard question.
Okay, so there is a problem with the fact that when we learn the GAN, or generative models or AI models, they try to simulate the data, but when you have the data, would you, for example, look at the images or books, the data is to some kind immoral. So if you use kind of NLP models, then if you ask what is a scientist, it's always a man. So because you learn on the books from the history. So the problem is the fact that we humans are immoral. I think that it's hard to solve. From what I know, the people who work at the companies are very aware of the problem that some models can be immoral because they are afraid that someone will sue them. And because of this, from the few years, we see that companies try to build models which are, in a sense, fair. But it's a very hard problem because the data in itself is not fair, and you try to make it fair. So, but it's being done. So I think that, in a sense, we will teach AI what is some kind of morality, but it's a hard problem.
Definitely, it is a very big problem. We do have 2 more minutes, so I think we can have one more extra question. So let's see the last question that we have here from our audience. What happened when we use GAN to crash discriminator and we create images with discriminator cannot recognize fake from real?
As Przemek said, so if you do this, so if you use GAN and we create images with discriminant cannot recognize fake from real, there are two situations which I think you can distinguish. So either they are really so good they are not real, but you cannot distinguish them. So this is one thing. And the second thing, I think, what would happen is you would create some kind of adversarial examples or something which is which the machine doesn't. You could create something which the machine thinks is real. The human can, from the first moment, recognize that it's very, very different. So I think that if you do that, you can obtain very strange results. So if you look, for example, at classifications, sometimes you can the networks can say that a guitar is an elephant, and I think that something like this would happen here. So there will be kind of misreality problem.
Okay, thank you very, very much. Thanks to Przemek and Jacek for their great presentation. Big applause for them.